In this video, we're going to talk about part one of the partial fraction decomposition. And in part one, we're just going to talk about setting up the decomposition. Okay, so when we set up the fraction decomposition, this is going to depend entirely, it depends solely on the types of factors that we find in the denominator. So before you even get started, you want to make sure that your rational expression or rational function is already factored, but just in the denominator. You leave that numerator completely alone. We are going to focus in part one just on the denominator. And so by types of factors, there's really four types of factors you're going to find. So the first one is if your denominator consists of some distinct linear factors. Okay, so distinct just means different, unique, and it's not repeated. Okay, so for example, we're going to have some kind of polynomial in the numerator. So I'm going to use p of x. Remember, this phase here ignores the numerator. It's all about the denominator. So I'm going to de-emphasize the numerator here. It's some kind of polynomial. But let's say in the denominator you have three linear factors and they're distinct. So x minus 1, x plus 2, and x minus 7. Okay, so these each individually are linear, right? You can see inside each of these parentheses that the factors themselves are linear. And the reason they're distinct is because they're all different, okay? None of them are repeated. It's one of these, and one of these, right? So when you have a denominator that consists of distinct linear factors, the setup, okay, this is just the setup. The setup is going to be that, you know what, this is a sum of three fractions whose denominators are these three distinct linear factors. Now, if I had 5 linear factors, I'd have 5 fractions over here. If I had only two factors, I'd have 2 fractions, right? And so those are the denominators. What I don't know are the numerators, okay? And the numerators in our setup are always going to consist of the unknown things we don't know, okay? And they're always going to be 1 degree less than the denominator. So each of these denominators is degree 1, less than 1, 0, right? So each of these is a constant. So A, B, and C. So we're going to be using letters of the English alphabet starting with A. We're going to use capital letters. It's going to make them stand out when we're working with our fraction decomposition. Okay, so when you're working with distinct linear factors, each different linear factor gets its own denominator, and then each numerator is just an unknown constant. These could end up all being the same number, they could be different, some could be negative. That's what we're going to figure out later. For now, we're just we're doing the setup. The second option is if you have linear factors that aren't distinct, right? They're the same, they're repeated. So repeated linear factors. Okay, so maybe it's all still linear, but some of them are repeated. So let's say the numerator is some kind of polynomial. We're not focusing on that. And let's say my denominator factors into x minus 1 squared times x minus 2 cubed. Maybe this one's repeated twice, hence the exponent, and this one's repeated 3 times. Okay, so you're going to know if these linear factors are repeated if they have exponents on them, right? So here, what we have to do is each of these factors is going to get its own denominator, but it's going to be repeated over here as well. So x minus 1 is repeated twice, so I don't know if this came from adding x minus 1 or a fraction with denominator x minus 1 squared. And if x minus 2 is cubed, I don't know if that came from x minus 2 to the first power, x minus 2 to the second power, or x minus 2 to the third power. Okay, so anytime these factors are repeated, you have to include not only the second power, but everything else down to 1. Not only the third power, but everything else down to 1, right? So I've got x minus 1 to the first, x minus 1 squared. That gets me up to 2. X minus 2 to the first, x minus 2 squared, x minus 2 to the third. That gets me all the way up to 3. So here I have 5 potential fractions that could be added together to give me this quantity. Okay. So the numerators, if each of these factors, ignore the exponent, okay, but if each factor inside the parentheses is linear, the numerators are just constants, a, b, c, d, e. Okay. The third option, is if I can't factor that denominator all the way down to be linear. Okay, because we only want to work with real numbers. Now, I know I could get down to linear factors always if I incorporate complex numbers, but we are not doing that. When you move on to calculus, you'll find calculus with complex numbers is, well, complicated. And most of what you learn in calculus 1 and 2 has to do with real numbers. And this is one of those cases we want to work with just real numbers. So what if I have a denominator that won't factor all the way down? Then that means I'm going to have some kind of quadratic that can't be factored unless I use complex numbers. So we leave it and we call that a prime, right? So if I have distinct prime quadratic factors. Okay, so again, distinct. So if I've got a quadratic factor that isn't repeated, it's only there once, maybe I have a couple of them or 3, and they're all different, okay? And then the last one we'll talk about is if some of these are repeated, okay? But yeah, so let's say I've got some kind of polynomial in the numerator, and then in the denominator, I've got x squared plus 4. And let's say maybe I've got x squared plus 3. So this is a prime quadratic factor. I can factor this using complex numbers, but I don't want those. Okay, so I can't factor this with the real numbers, so we call it prime. Same thing here. I can't do it with real numbers. So I'm kind of stuck here. I can't factor this all the way down to be linear. All right. So what we're going to do here is for each distinct prime quadratic, so each one of these, each of these is associated with a different fraction. So we copy each of those factors to be the denominator, okay? And then the numerators we don't know, that's what we'll have to solve for eventually. The numerator is always 1 degree less, okay? So since these denominators are degree 2, the numerator will have to be degree 1, which means it's going to be linear. So I don't know ax plus b. Okay, it's got to be linear. So there could be a coefficient on x, and there could be a number that's added or subtracted, right? So this is going to be my unknown linear factor up here. So same thing here. Denominator is degree 2, so the numerator will be degree 1. So cx plus d. Make sure you don't repeat any of these letters because later when you're solving, it's going to get confusing which one is A. So make sure you just keep going through the alphabet. Just each one of these gets a new letter. Okay. And then the fourth case is repeated prime quadratic factors. Okay, if your quadratic can be factored down to linear things, you want to, because not only will it make your life easier, but it will make your work correct. Okay, so this is only if you can't factor it any further. So this time we're going to have them repeated. So I've got some kind of polynomial in the numerator. And in the denominator, let's say I have a quadratic factor, prime, x squared plus 4. Let's say this is repeated twice. And why not? Let's do one more. How about x squared plus 3? This one is repeated 3 times. Okay. We're going to do the same thing as we did with the repeated linear factors. Okay. So I need to pay attention to these exponents. So since this factor is repeated twice, then I'm going to handle this factor here once and this factor here twice. Okay, because there's a couple ways I could get x squared plus 4 here twice. All right, so we're handling all the cases in our setup. This quadratic factor is repeated 3 times. So I need it in the denominator once, twice, and then 3 times. Okay, so first power, second power, third power, all the way, all the time. If this was repeated 7 times, that would give me 7 fractions. I'd need this here once, twice, 3 times, 4 times, 5 times, 6 times, and 7 times. Okay. Now, because each factor inside the parentheses, okay, inside the parentheses, each of these is quadratic, that means each numerator will be 1 degree less. So these are all going to be linear. So ax plus b, cx plus d, ex plus f, gx plus h, ix plus j. Okay. So this is the setup. This is what we're going to be doing in our setup, is we're going to be putting in these a, b's, and c's in the numerator, okay, and maybe ax plus b, cx plus d. And what I really need you to be focusing on is what's in the denominator, okay, because later in part 2 and 3, we figure out what a, b, and c are going to be, all right? For now, I need this setup. So let me show you an example with some numbers. So let's say we have, for example, this rational expression. So I have 2x plus 7 divided by x minus 1 times x plus 2 squared. And I need to set up the partial fraction decomposition. And maybe that's all I need to do is just set it up, right? So I have one distinct linear factor, and I have a repeated linear factor. Oftentimes you're going to have some kind of combination of these, right? So the distinct linear factor, this one single occurrence, it's never repeated again, this gets its own fraction. So x minus 1 down there, 1 degree less is just a constant. Plus, this factor is repeated twice. So I need it here once, and then twice to the second power. And again, each of these is linear. If you just look inside the parentheses, ignore the exponent on the outside, right? Each of these is linear. So each numerator is just a constant b and c. And that covers all the factors in the denominator. So this would be my setup. Let me show you one more. Okay, so I want to set up the partial fraction decomposition for this rational expression. I notice I have a linear factor repeated twice, and I have a prime quadratic only here once, okay? So this first factor here is linear, it's repeated twice, so it's going to give me 2 fractions. X plus 2 to the first, x plus 2 squared. Because each of these are linear, the numerator is 1 degree less, so constant, constant. This is a prime quadratic, only here once, exponent 1. So that gives me one more fraction. The denominator is that. And because this is quadratic, degree 2, the numerator's degree 1, which means it's linear. So cx plus d. And that would be my partial fraction setup.